on the AQUAEXCEL project. So our first speaker will be Professor Chen. He's from the University of Surrey in the UK. He trained as a process control engineer and is an expert in process modeling and optimization with particular applications to agricultural, biochemical and pharmaceutical processes. His research has received funding from lots of different sources, such as the UK Research Council's EU Horizon programs and also industry. And that it also includes a BBSRC grant in using models and data analytics for optimizing the productivity of aquaculture, and also a new 4 million grants in which he will lead the model-based optimization of biomass production under controlled environments. He currently leads a group of 3 postdoctoral and 8 PhD researchers and has published over 100 peer-reviewed journal publications. So today he's going to present the outcomes of his AQUAEXCEL3.0 project. It's called Adventure, which is about computer modeling to assist aquaculture production. So Tao, the floor is yours. Please go ahead and share your slides.
Yes, thanks very much for the very kind introduction. So I'm trying to share my screen. I hope that's all right. Everyone is able to see it?
Yeah.
Okay,
perfect.
Great. Yeah, well, again, as Marita, you have introduced, I'm Tao Chen, and I work in the chemical engineering department. You may wonder, what is chemical engineering to do with aquaculture, to do with fish farming? But actually, from our perspective, we kind of view aquaculture as a general biomedical process, biochemical process, if you like. So essentially, you are trying to grow biomass in response to the various environmental parameters, and you are trying to find the way to optimize those environmental parameters. So this is where we are coming from. And particularly, my expertise is in computer modeling to assist the production monitoring, prediction, and optimization. And that is going to be the topic that I will talk about today. I have to declare that a lot of this work that I'm going to talk about has been funded by AQUAEXCEL, but in the same time, because of the COVID restrictions, our original plan to conduct experiments with our collaborator in this project in Hellenic Center for Marine Research in Greece was not able to go ahead, and therefore some of those contents are coming from the BBSRC project mentioned by Marika, where we try to apply modeling and the digital technologies to assist aquaculture production. So I'm going to go ahead and starting from the so-called knowledge need. I guess over the years we've seen a sort of a trend where I wouldn't say we move from open pond to research rating aquaculture systems, but actually we've seen a lot of increase of application of moving from an open fish farming processes into a more controlled environment. And because we operate more and more in a controlled environment, we're able to implement a lot of modern digitalization and automation technologies. And therefore that will allow us to relieve a lot of labor-intensive activities. So our argument is the infrastructure is already there. Infrastructure is being modernized, and you have modern sensors, you have modern software, you have modern communication technologies that will allow you to get a lot of data from the aquaculture production. Then the question becomes, how do we turn the data to actionable information? Here comes the data-driven approach. Obviously, with the surge of machine learning, artificial intelligence, you can do a lot of machine learning approaches to this data you collect. But then in the same time, it is about how to make an optimal decision. Once you have this data, once you have this information that we are connected from the real-time operation of this aquaculture systems. So we propose our solution, which is a so-called digital twin. So digital twin, if you look at the literature, can mean many, many different things to many, many different people. But in our context, we are trying to propose an approach where we are not just looking at the data coming from the process, but we're also trying to encode the mechanisms of fish growth of the water chemistry into a mechanistic model. And we combine such a mechanistic model together with online data, whatever data we can get from the production process, we put them together into a computational engine, and that is what we call a digital twin. So with this digital twin, we are making a linkage, if you like, between our models, computational models, with the underlying aquaculture facilities supported by the sensor technology, supported by the data transmission technology, and we help to make decisions. And by making decisions, I mean, we're trying to do primarily two different things. One is, are we able to estimate some of the critical parameters that are not always or not easily measured in the real-time production? Say, for example, nitrate and nitrite concentrations in agricultural system, total nitrogen, which we know that there aren't many reliable sensors on the market that requires minimum human effort. And then how do we optimally decide the feeding and the water quality control decisions? So those are the two things that we're trying to address in our research and in our project. So without going into too much details, I'm going to show a few examples. Don't worry too much about the flow diagram. I just want to point out a few things through the three different examples. The first one, the center of the first example is where we have a mechanistic model that helps us to link together the water chemistry and how this total nitrogen is being affected by how much feed you put into your system, how much is being consumed by the fish, how much is left over by the fish, and how much is excreted by your fish. Right? So once we have this mechanistic model is able to give us a prediction of the total nitrogen concentration in the system. And to start with, the prediction is not going to be very accurate. But what we can do is we can link that model, mathematical model, together with offline measurement, very infrequent measurement, once a day, once a few days, once a week, help us to calibrate this model to correct the prediction. And therefore, our prediction of this critical parameter becomes more and more reliable when we move along the time. So that's the first example, as I said before, trying to estimate the critical parameters and variables to help us monitor the production process better. And the second example is where we get a lot of data from the BBSRC project mentioned before. Those are data from the actual production system in a fish farm in China. Because by the way, that project was a collaborative UK-China 2 million project trying to bring people together from the two countries to look at aquaculture. And once we get this data, which tells us how the decision is being made in an actual RAS system to cultivate a certain fish species, we're trying to turn this data into the information that allows us to predict when we go from day 0 into 1 month ahead of the time, how this fish is going to grow from a baseline weight into a certain weight, and we can see a fairly reliable prediction between the model and the actual measurement being conducted in the actual facility. So this illustrates that when we have sufficient amount of data, that does allow us to build a computer model to help us make predictions. And then finally, if we don't have such a type of data, then again, we go back to the so-called digital twin approach, where we link this mechanistic model together with online, some infrequent measurements, so that we can make decisions in terms of when and at what amount we should feed to the fish. So therefore, we can reduce the time of the fish cultivation to meet the market required biomass weight as soon as possible. So this, I hope, have given you a sort of flavor of what we do to link the mathematical model to help us make decisions. In terms of a target market, we can easily think of agricultural producers. If we have the software available and fully validated and tested, then we should be able to deploy the software tools to help the agricultural producers to make continuous monitoring of the process parameters I mentioned before, and to make optimized decision-making in terms of feeding, in terms of water quality control, and so on and so forth. And then we also believe that rather than us in academia to push this to the market, we can collaborate with a technology service provider. And in the project we mentioned before, we actually work with a control software provider to help us implement some of this academic research and findings into their software. And they're trying to embed the algorithms together with the hardware solutions to support intelligent aquaculture operations. And then I guess in terms of results and impact, if we do that, if you have this digital twin, obviously, as we mentioned before, we can potentially improve the productivity by increasing the amount of fish you produce within a certain amount of time within the constraint of your resources. We can improve the process monitoring, and we can make more proactive troubleshooting. You can look a few days, a few weeks ahead of time, what potential can go wrong, and make mitigation strategies well in advance. And finally, the capability to predict, how much fish you are going to produce and at what time. You can link that information potentially with your supply chain, your downstream, upstream operations. This will help you to decide, how much of fish feed you are going to source from where, and then how much of the fish you are going to produce to push to the market. And this, we believe this integration with the supply chain will help the business as well. But having said that, I have to admit that the current TRL is fairly low. We are still at the applied research level. A lot of those results, because of COVID, were based on simulations. We have a bit of retrospective data to validate certain elements of our research, but still at the methodological development stage. And we believe further development, we would like to push this into a more applied research, lab scale test, and even to the full scale test to push it to higher TRL level. And hopefully we will be able to collaborate with more commercial partners in the UK, in Europe, to help to make this, more into a more mature stage. And yeah, that's me. And this is my contact email. And hopefully my presentation, will open up the door for more collaborations in the future. And thanks so much. And I hope I'm doing okay with my time. Thank you.